Good day to everyone. I'm glad to welcome you all to our course on microservices architecture. This will be an intensive journey consisting of 11 lectures during which we'll explore the aspects of developing microservices. In this course of lectures, we'll look at different topics related to microservices development. We'll start with what microservices are and how they are different from monolithic architecture. We'll look at how to decompose large services into smaller ones and which approaches exist, what types of communication there are, and how to communicate between different services, how to handle transactions in microservices, different patterns that we can use, what resilience is and which patterns help to achieve it. We'll look at tools for deploying microservices as well as different deployment strategies, how to quickly scale our services and which approaches exist, how to effectively monitor all these zoo and quickly detect failures. And finally, we'll discuss security in microservices architecture. This course is designed to be useful to a wide range of specialists. First of all, it's aimed at junior and middle developers who want to understand microservices and its implementation in depth. It will also be interesting for system analysts who want to better understand the technical aspects of system design to work more effectively with business requirements. Even for seniors, this course can be a good opportunity to refresh knowledge. So, let's begin. We'll start our first lecture, which will be about the evolution from monolithic to microservices. We'll look at why microservices architecture is needed at all and what factors make companies move to it. Okay, before going into the world of microservices, it is important to understand what software architecture is in general. There are many definitions, but we can describe it like this. Architecture is the system skeleton and rules, what parts exist, where they sit, how they talk, and the big choices, languages, protocols, boundaries that shape all future code. As Robert Martin said, good architecture makes the system easy to understand, easy to develop, easy to maintain, and easy to deploy. This is about the fundamental basics, which, like the foundation of a house, are hard to change when the system has already grown. The history of software development is a constant evolution driven by growing business needs and change in team organization. We started with monolithic architectures, where all the code was in one place. Such systems were relatively simple to deploy and monitor at early stages. But as the project grew, monoliths became harder to maintain, expensive to scale, and slow to deploy. The biggest problem was that teams started to block each other, working on the same codebase, which slowed development and required many agreements. These challenges lead to evolution. The next step was service-oriented architecture, or SOA, which allowed splitting some services but still remained heavy. Later come microservices. They solve many monoliths problem. Teams work independently, each microservice has its own database, enabling fast and independent deployment. This allows team scaling and faster feature delivery, as independent teams can work in parallel with fewer blocks. Other approaches also appeared in the evolution of architectures, such as nanoservices or serverless functions. A nanoservice is a minimal microservice that performs one business action and lives separately, its own repository, pipeline, or process. It gives fast independent scaling and deployment but increases network costs and DevOps complexity. Microservices become the balanced and widely used solution. Let us look at monolithic architecture. This is the foundation where most applications start their development. Imagine it as one self-contained block of code where all the program functionality is combined in one codebase and deployed as one process. This means that the whole application, from the interface to the database logic, is in one place. Usually, this is one code repository. Here we can see a typical monolith where the user interface, business layer, and data interface run in one process as a single whole. About pros. Communication between components in a monolith happens through method calls, not through the network. Second, easy code reuse. You do not need to think about shared libraries or code duplication because all code is in one place. This removes the need to manage dependencies and distribution of shared components. Third, a limited set of technologies. This means that all people in your company know how to work with this technology stack. If someone does not know, it is easy to teach them. And last but not least, simple deployment and monitoring. For monitoring, there is no need to track network calls between components because they do not communicate through the network. This removes the complexity of distributed tracing and monitoring, which is typical for microservices. Now let us move to the problem that always appears when a monolith grows. First, it is harder to keep the codebase clean. Your team is not separated from each other, and if someone wants to use an undocumented feature or do something outside the public interface of your model, they can. This quickly breaks rules and architectural principles. Second, teams start to block each other. This appears as conflicts during releases when chains of one team block others, or as arguments about choosing shared libraries and frameworks. Third, scaling becomes expensive because you cannot scale only one part. If there is a problem in one component, you must scale the whole monolith, which is not efficient. This is also related to long deployment because the service has many dependencies as it's one big unit. Another big disadvantage is poor fault tolerance. Since there is one shared codebase, one error in one place can make the whole application crash. Okay, then smart engineers understood that processing everything in one process is not efficient with high loads. So another approach was developed. Service-oriented architecture is an approach where software functions or services are split into smaller, coarse-grained components. The main ideas in SOA are service reuse and using an enterprise service bus. SOA features. SOA is centrally managed architecture. You can imagine it as an orchestra with many players but all controlled by one conductor. For communication between services, especially if they are built in different programming languages, SOA uses Enterprise Service Bus. And SOA aims to share services and resources. This can include shared data storage between services. Here we have like four main types of services, each with its own role in the system. Business service. This service performs main business operations. In an online shop example, a business service can be shopping cart or product catalog. Enterprise service combines the functionality of application and infrastructure services to run big business processes. For example, an enterprise order management service that coordinates order processing, checking product availability, payment, and logistics. Application service. Main functionality of a specific function. These services cannot be reused for different tasks, or they are limited to a specific context, but they can be embedded into higher level services. And the last one, infrastructure service. Non-business or non-technical operations. This is a group of easily reusable services. Examples include authentication, authorization, sending SMS or email, and logging. Good. We have already talked about SOA architecture, which was the answer to monolith limitations. Now, let us look deeper at the microservices concept, the next evolution step and the most common SOA implementation today. There are many definitions of microservices, and one of them states microservices architecture is an approach to software development where a large, complex program or application is broken down into small, independent services. It has several important points. First, components are implemented as separate services. Second, the composition is based on business needs by domain specifics. Instead of splitting the app into layers like presentation logic, business logic, persistence layer, we create services like payment service, user service, or delivery service. Third, decentralized work with data. Each microservice usually has its own database. This gives independence but also challenges. For example, for analysts who need to collect data together. Fourth, high automation level of infrastructure for maintenance and deployment. Since microservices usually have dozens, hundreds, or even thousands of horizontally scaled services, manual control is impossible. Fifth, the system is designed from the start to handle failures, especially network-related ones. Microservices are less stable than local calls, so they are built to survive service crashes. The ideal size of a microservice is such that one team can rewrite it in 2 weeks. The team here means a two-pizza team, a concept by Jeff Bezos, meaning a team small enough to feed with two pizzas about 5 to 8 people. After looking in detail at the disadvantages of monolithic architecture, let us now focus on how microservices solve these problems. Team and development independence. In a monolith, teams often block each other because they work on one codebase. Microservices allows teams to work completely separately. Each team is fully responsible for its service, can choose its own technologies and way of implementation, and most importantly, can release when it wants. This makes business processes faster. Second, fast and independent deployment. In a monolith, deployment was long and complex because of many dependencies and large code. Microservices allow deploying each service separately and very quickly. Third, simple component development. The codebase of a typical microservice can be rewritten in 2 weeks because it is small, easy to understand, and does not collect too much extra code. This is very different from a monolith where keeping the codebase clean was much harder. This side fits the two-pizza team concept, 5, 8 people working effectively on one microservice. Fourth, scaling only the bottleneck. In a monolith, scaling was expensive and not precise because you had to scale the whole platform, even if the problem was only in one component. Now, if you see that a specific microservice is the bottleneck, you can scale only it without touching the rest. This saves resources and costs. The system with microservices is designed to survive failures, especially network-related ones. If a monolith crashed completely because of one component, in microservices, failure of one service does not stop the whole system. This is possible because of separated data management, where each microservice has its own database. Local optimization. Microservices allow choosing the best technologies, programming languages, or databases for a specific solution. For example, for a service where consistency is critical, you can use PostgreSQL. And for a comments service where speed is more important and some data loss is acceptable, you can use, for example, MongoDB. This flexibility is not possible in a monolith with a unified stack. Okay. We have seen how powerful microservices can be for scaling teams and speeding up development. But like any architecture choice, microservices bring their own difficulties and problems, which you must know and manage. For every good decision, there is a price to pay. Okay, first, complex network communication. In a monolith, you just call a message. In microservices, each request is a network call, which can be unpredictable. Second, difficulty in keeping data consistency. In a monolith, all data is usually in one database, so consistency was simple. In microservices, each service has its own database. Local consistency is easy, but distributed consistency needs more complex mechanism. This is one of the hardest part of microservices. Third, complex monitoring. In a monolith, monitoring was simpler because all code was in one place. In microservices, with dozens or hundreds of services, you need request tracing and distributed logging to see what is happening. First, code reuse difficulty. Code like logging or HTTP client handling is needed in every service. This means you need to create libraries and then distribute and support them. Fifth, complex integration testing. Because you now have many separate services talking through the network, more components must be started for testing. They will also communicate over the network, making end-to-end tests longer and more expensive. Technology zoo. Microservices allow technology freedom, but this can result in every service being in a different language or framework. This makes moving a specialist from one team to another harder because they need more time to learn the new stack. Good. We have talked about advantages and disadvantages of microservices, but when choosing an architecture, non-functional requirements are key. They define how the system works, unlike functional requirements, which describe what the system does. They are the criteria we use to decide which architecture fits best. Let us look at some of them. Scalability. Very important for growing systems. Here we have vertical scaling. Means making one server stronger by adding more memory or CPUs. And horizontal scaling means adding more instances of your application, processes, or containers. Resilience. The system's ability to stay available and working during failures. In a monolith, if something fails, most likely it will all stop working. In microservices, only some functionality stops, and the user may not even notice. Maintainability. Easy of support, updates, and fixing bugs. Microservices are easier to maintain because you can rewrite one microservice in 2 weeks, keeping it small and understandable. In a monolith, it is harder to keep the codebase clean. Usability. How easy and effective it is for a user to work with the system. Durability. Data is not lost even after failures or restarts. Once an operation is confirmed, the data is saved and will not disappear. Security. Protecting the system and its data from unauthorized access, use, disclosure, change, or destruction. Often has trade-offs with performance because encryption needs extra resources. And performance. How fast the system works and processes requests. Okay. Sometimes microservices are not the best choice. Remember, there is no silver bullet. Every solution has a cost. The architecture choice must match your specific context and business needs. When a monolith can be better? At the start of a project, for startups or MVPs. Speed is more important than perfect architecture. Microservices bring too much extra work at this stage. For small teams, if you have only 2 or 3 developers, it is too early for microservices. No DevOps and automation. Microservices needs a lot of automation and DevOps skills. Without good deployment, monitoring, logging, and tracing processes, managing many microservices becomes chaos. High migration cost. Moving from monolith to microservices is expensive and long. If your problem can be solved by just adding resources to the monolith or making a small refactor, that is often cheaper and safer. Okay, we have looked at key points of each architecture, including pros and cons of monolith and microservices. Now let us imagine a typical user registration scenario with an email confirmation. We will see how it could evolve in different architectures. In a monolithic architecture, as shown in the first diagram, all functions are in one big application. When a user registers, we validate the data, save it in a database, create an activation key, and call the internal email sending service function to send the confirmation. In SOA, as shown in the second diagram, services are logically separated. The REST service gets the request and sends it to the enterprise service bus, the coordinator. The ESB sends it to the validation service, gets the result, sends it to the user service to save the data, and then to the email service to send the message. These services can run separately and may share one database. In microservices, as shown in the third diagram, it is more flexible and scalable. For simplicity, the API gateway is not shown. The request first goes to the user service, where it is validated. If all is OK, the user is saved. And the mail service is called, which creates the activation key and sends the confirmation email. To finish this lecture, let us summarize the main ideas. Architecture choice is always a reasoned decision based on business needs, non-functional requirements like performance, security, scalability, and team resources. Monolith is a great start for most projects because it is simple to deploy and monitor. As the organization grows, microservices solve scaling problems, allowing independent teamwork and improving fault tolerance. But they bring new challenges like network communication, data consistency, testing, monitoring, and technology diversity. There is no silver bullet. Every solution has a cost in money, time, or complexity. Evolutionary architecture is key. Your system should be able to change, be replaced, or be modified to adapt to new needs and opportunities. Good. After each lecture, I will give you a quiz to help remember the material and make it more interactive. You can scan the QR code on the slide or use the link in the description below this video. And thank you for your attention. If this was useful, don't forget to like the video and subscribe to the channel. You can also find my LinkedIn, Medium, and Telegram on the slide and in the description. Feel free to connect, follow my articles, or text me if you have any question. Bye bye.